What's up, everybody? My name is Demetri Kofinas, and you're listening to Hidden Forces, a podcast that inspires investors, entrepreneurs, and everyday citizens to challenge consensus narratives and to learn how to think critically about the systems of power shaping our world. My guest in this episode is Chris Miller. Chris is Associate Professor of International History at the Graduate School of Global Affairs at Tufts University. He is also the author of a new book out tomorrow titled Chip War, which chronicles the history of a decades-long battle to control what has emerged as the modern world's most critical resource, the microchip, and the commercial industry that supports it. Chris and I spent the first hour of our conversation discussing the technological, commercial, and distributional characteristics of the existing semiconductor supply chain, the various steps involved in the production process that stretches across various companies and geographies, the incentives that operate in the industry, the technological imperatives that inform investment decisions, things like product life cycles and capital requirements, and the role of government subsidies and regulations, all of which help to explain how the industry has evolved to look the way that it does today, a globalized and highly efficient network that is more vulnerable than ever to geopolitical disruption. The second hour is where Chris and I focus our attention on the geostrategic dimensions of chip competition, the steps that are being taken to reorganize the industry, the efforts being made to build resiliency into various parts of the supply chain and production and manufacturing process, and what the main challenges are to doing that successfully for not only the United States and its allies, but for China as well. My goal in this conversation is to bring clarity to a subject that has not only captivated the public interest, but which increasingly determines the national security priorities and strategic investment decisions of the United States, its allies, and partners, and which forms the foundation of virtually everything that we associate with the modern world. For anyone new to the program, Hidden Forces is listener-supported. I don't rely on advertisers or commercial sponsors. So if you want access to the second hour of today's conversation, as well as the transcripts and intelligence reports, which include my takeaways from every episode, as well as my thoughts on what comes next, head over to hiddenforces.io, select the episode that you're interested in, and click on the premium extras, where you can then sign up to one of our premium content tiers. If you have questions about our Genius tier, which includes access to the Hidden Forces community, Q&A calls with guests, in-person events and dinners, feel free to send an email to info@hiddenforces.io, and I or someone from our team will get right back to you. And with that, please enjoy this incredibly informative and timely conversation with my guest, Chris Miller. Chris Miller, welcome to Hidden Forces.
Thanks for having me.
It's great having you on, Chris. You've written a great book. I was telling you that I really enjoyed it. And there were two episodes that came to mind for me while reading the book. One was our recent episode with Sebastian Malaby on the history of the venture capital industry, because a lot of your book, at least the very beginning, is about the history of the semiconductor industry with its origins in the United States and with companies like Fairchild Semiconductor, Texas Instruments, and Intel Corporation. Before we get into any of that, though, I'd love to know a bit more about you and what led you to write a book about the history and geopolitics of the semiconductor industry, given your background as a scholar of Russian history and Russian foreign policy.
Yeah, that's right. I'm trained as an economic historian who focuses on Russia, which is, I guess, not the most natural way to come to write a book about the history of chips. But I started this book trying to understand why it was that during the Cold War, the US and the Soviet Union both had comparable ability to make nuclear weapons, had comparable ability to produce rockets and send people into space. And in fact, the Soviets got the first satellite into space and the first person into space ahead of the US. But the Soviets could never find a way to miniaturize computing power. And this fed into their economy and created huge problems economically, but also was really fundamentally important in why they began to fall behind militarily. And so I started digging into this history of how do you miniaturize computing power? And at the core of this question is the invention of the computer chip. And I came to realize that the US's role in inventing the first chips and the role the US plays today, standing astride the global chip industry, is really crucial not only for the history, but also for understanding the present day.
That's interesting. I always wondered about that because the Soviets were early leaders in the space race, and they had a lot of brilliant theoretical physicists. So what was it that accounted for the advantage that the United States had over the Soviet Union?
Yeah, you're right. It certainly wasn't scientific expertise that the Soviet Union lacked. And if you actually look at some of the early Nobel Prize winners in semiconductor physics, you'll find a number of Russian and Soviet scientists who won Nobels in the fields. They had a lot of smart people working on the problem. What they didn't have was two things. First, they didn't have a consumer industry that was nearly as big as the US. And although the first chips were made for military purposes, very, very quickly after, US chip firms in Silicon Valley and elsewhere began focusing on consumer applications, such that by the 1970s, most chips were being sold for corporate computers or for consumer devices like calculators. And that provided a vast market that helped fund a lot of the innovations that drove the chip industry forward. And the second thing the Soviets lacked that the US also had from day one was an international supply chain. US firms could sell to customers in Europe or Japan, the world over, and they could also buy components from those countries as well. And so US companies were able to buy machine tools from Germany or buy chemicals from Japan. They were able to also import engineers from places like Italy or France. And some of the key innovations in the chip industry came from foreign-born engineers working in Silicon Valley, whereas the Soviets had hardly any of that. They could rely on machine tools from Bulgaria or Hungary, which were just far less advanced than what the US could get from Western Europe or Japan. And they had almost no immigration into the Soviet Union except for a couple of spies. And so the global focus of the US chip industry was a huge asset in terms of expanding the market of customers and expanding the amount of specialized materials and tools that Silicon Valley had access to.
You know, that's fascinating. And it makes me think a bit about the challenges of what we're seeing now, and what we'll talk about, which is this reshoring or onshoring or friendshoring, and how the move from efficiency to resiliency will impact the quality of products in the industry and innovation, et cetera. That's something that I'd love to talk to you about. How would you describe what this book is about to people that have never heard of it before?
The book argues that you can't understand the modern world without understanding the role computer chips have played in every major trend, whether it's the balance of military power, whether it's the shape of globalization, whether it's the growth of complex supply chains, whether it's the rise of China. Today, all of these major trends have at their core semiconductors. And if you look at the balance of power today in the world, if you look at the distribution of wealth, all of these are shaped by the struggle to control the most advanced computer chip technology. And if you're someone like me, who when I started this book had only a vague awareness of what a chip was, to say nothing of how they're produced, it's difficult to understand, I think, a lot of these trends. And it's only when you dig into how complicated it is to make a semiconductor and how a tiny number of firms and countries control their production that you begin to understand the balance of economic and political and military power in the world today.
So this also raises something that I thought about when I was reading your book, because yes, so much of this book is about all the things that go into the production of semiconductors, all the steps involved, from sourcing materials to R&D to design to production to assembly. But behind all of that is this larger geostrategic competition between the US and China. And I'm curious how different your book would be if you had written it in a unipolar world. And I don't mean if you had written it in 2000, but what I mean is that you would have written it today, but if the world had geostrategically looked very different, how the emphasis would have been different. How has that informed your book and what you focused your attention on?
There are two key trends in the chip industry today, which are driven by the geopolitical competition between the US and China. One of them is that the US is trying very hard to restrain China's technological growth. We've seen this with bans on export of certain types of chips, certain types of software, certain machine tools to China. And the goal is to slow China's technological progress, which is a goal the US didn't used to have. For a long time, the US was trying to promote China's technological progress as part of economic integration between the two powers. But now that's changed, and the US has a zero-sum approach to Chinese technology. That's one factor that's driven by the competition. Second is that China is pouring many tens of billions of dollars into a tremendous effort that is really unparalleled in history to domesticate chip technology. Today, China spends more money importing chips than it does importing oil. The Chinese leadership is deeply fearful that this gives the US leverage over China that can be used both during peace and during wartime. And so they're desperate to find a way to produce the technology they need domestically. And this is going to reshape the chip industry. And if it succeeds, which is still an if, rather than something that's guaranteed, it would also reshape the balance of military power.
So, Chris, one of the things that I'm aware of, or I've become increasingly aware of in having had so many of these types of conversations, and actually the next conversation I'm having tomorrow is with Michael Beckley and Hal Brands on the specific issue of Taiwan. And Taiwan is a central part of your book as well because of TSMC and the important role that, the really outsized role that the island has in the production of this critical, you could call it a commodity. I'm actually curious to know what you would call it, because in some sense it's a commodity, but it's clearly not a commodity because not all chips are made the same. The thing that I've become acutely aware of is that I've done so many shows on this, and so many people have become aware of the issues, and they hear conversations about it, and thousands and hundreds of thousands, or God knows how many articles are written about it. And yet I think very little time is spent trying to really get clear on what's at stake here. And I'm curious to know what you think is at stake here, that we should be devoting so many resources, so much public investment to change a model that has, by any reasonable measure, been working extraordinarily well and has created unbelievable levels of economic growth and advancement over the last 60 years or so, since at least the early commercialization of the first integrated circuits.
I think there are two big risks for the United States today when it comes to chips, and not only for the United States, but for much of the world. The first risk is that if there's a war in the Taiwan Straits between China and Taiwan, it won't just impact production in China, it'll impact production in Taiwan and Taiwan's ability to export. And today, Taiwan produces around 1/3 of the new computing power we rely on each year. It produces 90% of the most advanced processor chips. And without Taiwanese production, entire segments of industry would just grind to a halt, from autos to smartphones to high performance computing. And this is something that's new. If you rewind a decade, our reliance on Taiwan for advanced chips was substantially lower, and our reliance on chips was also lower as well. But as more and more devices have semiconductors inside and need computing power, and as Taiwan's role has increased and the significance of TSMC in particular has increased, the entire world's dependence on peace in the Taiwan Straits has increased alongside that. And this has happened just as the military balance in the Taiwan Straits has shifted in China's favor dramatically over the past couple of decades, thereby increasing the risk of war. So we've become more reliant on Taiwan, even as the risk of war around Taiwan is at the highest it's been in 25 years, if not longer. That's the first risk. The second risk is that China's government-led investment into its own semiconductor technology, if it succeeds, and to the extent that it succeeds, will not only reshape the commercial balance within the chip industry, it will reshape the military balance of power. Today, the US military and the Chinese military are investing very extensively in technologies like autonomous systems, advanced electronic warfare that are hugely dependent on semiconductors for processing power, for memory, for signals processing. And the militaries that are able to apply the most advanced chips to their systems will have the most effective military systems. So China's investment in domestic chip making will have a direct impact on the military balance of power as well. And 20 years ago, we didn't really need to worry about the military balance of power because the US was so far ahead. That's no longer the case. And China is catching up precisely in the types of systems that it's able to apply advanced chips to. So if China's chip investments succeed, and to some extent they are succeeding, we can discuss the details of that, but they're working to some extent. China's military will get more powerful. And as China's military gets more powerful, the risk of war in the Taiwan Straits grows, which increases the risk that the entire world faces a disastrous disruption to semiconductor supply. I think that's what's changed compared to a couple of decades ago, which is why the system that, as you say, has produced tremendous increases in the availability of computing power is now looking much more fragile than it would have a decade ago.
So this might sound like a stupid question, but I want to try to articulate it as intelligently as I can, which is, why is it such a big deal if China increasingly dominates, not necessarily dominates actually, because I guess you could make the counter argument that it's good for us to have this level of economic interdependence because the importance of Taiwan makes it a dangerous place to actually have a war. Because if the Chinese damage TSMC, for example, its production facilities, that's going to impact everybody. And it's to significantly impact economic growth, as well as all the military systems that all these different countries depend on. So why is not leaning into economic interdependence actually a better strategy, which, by the way, was the working model and theory that American foreign policy strategists were trying to implement for the last however many decades?
Yeah, there's a strong argument in favor of this idea that if we've got deep interlinkages, we've got a sort of mutually assured economic destruction, kind of like the mutually assured nuclear destruction during the Cold War. That thesis only holds to the extent that we think Chinese leaders are focused on maximizing GDP or focused on their economy, and to the extent that we think they fully understand the interlinkages that are in the semiconductor industry in Taiwan. And I would say 2022 is a year where we've already got one good example of a dictator being fed bogus information by his security services and launching a disastrous war that has imposed huge costs on his own country as well as his neighbors. And I think the Germans and Europe in general bet on economic interdependence for several decades to restrain the Russians, and it worked for several decades until it didn't. So I think the case of Russia is a reason that we should be skeptical or ask tough questions about the theory of mutually assured economic destruction. Whether it applies in the case of China and Taiwan, I think I'm less confident than I used to be. For 4 decades after Deng Xiaoping consolidated power in China, it was pretty obvious that Chinese leaders were focused on GDP growth above all. And you could even track, for example, the promotions of provincial governors in China. And the governors that had the highest GDP growth in their province got promoted the fastest. But for the past couple of years, that's changed. Xi Jinping has cracked down on his country's private tech sector in a way that was really costly for financial markets and GDP growth. He's pursued a zero COVID policy for the past 2 years, which has been devastating for the Chinese economy. And if you just think about it, China could have imported high quality foreign vaccines 18 months ago and been done with COVID. And instead, because they're unwilling to import foreign vaccines, they've had to pursue this zero COVID policy with ruinous effects on GDP growth. So I think the thesis that under Xi, China's leaders are fixated on GDP growth like they were under Deng or Jiang Zemin or Hu Jintao, that doesn't look like it fits the evidence today. And so the more that Chinese leaders focus on their own political power at home or nationalistic pursuits like domestic vaccines rather than foreign vaccines, the more I worry that actually maybe they're not calculating in terms of dollars and cents on Taiwan. Maybe they've got other more kind of visceral nationalistic interests in mind. And that's the type of leader that might be willing to roll the dice, gamble with economic consequences to try to retake the island.
Do we have any idea how the zero COVID policies have impacted China's own timeline for catching up with or surpassing the United States in some of these critical technologies and in their efforts to onshore as much of the supply chain as possible?
I think we've got to assume that the impact is negative. How negative it is, I'm not sure. We certainly got good evidence that the number of foreigners in China is declining, and China's chip development goals have depended very heavily on attracting skilled foreigners from Taiwan, from Japan, from Korea, from the US. other countries to work in their chip industries. Now it's a lot less appealing to live in China than it was a couple of years ago, especially if you're a foreigner because of the travel restrictions. I think also the private tech firms have been under a fair amount of pressure over the past 2 years, both because of the COVID restrictions and because of the economic effects that they've caused. And the more that China cracks down on its private sector or creates conditions where the private sector can't succeed, the harder it is to attract market-led participants into the chip industry. There's a lot of people in the chip industry in China that are solely focused on receiving government subsidies, but actually technology has been driven forward in China when it's succeeded by people who want to reach consumer markets or corporate markets. And the less effective the Chinese tech sector is in terms of focusing on consumers, the harder it's going to be for China to actually develop the technologies that it needs.
So let's take a step back now and build a foundation, beginning with the technology itself, to help people sort of understand as best as possible in the course of this interview what the contours are and the incentives are that have structured the business imperatives of this industry and the economic and technological outcomes. So let's start first with Moore's Law. What is it at the heart of the semiconductor industry and of chip design and manufacture that has allowed for this persistent, relentless doubling in computing power and increases in efficiency and miniaturization to the point now where there are components in the manufacturing process that are smaller, as I understand it, than even a coronavirus, which I don't understand. So I would love for you to help me understand that and our audience as well.
On each chip are transistors, tiny electrical circuits that turn on and off. And these circuits, as they turn on and off, create the ones and zeros that undergird all computing and all software. The first chip that was commercially available in the early 1960s had 4 transistors on it. Today, if you buy a new iPhone, the main processor, and there are several different chips on an iPhone, but the main processor alone will have over 10 billion transistors on it. So from 4 to 10 billion, that's been the increase in computing power. And that's only been possible because it's been feasible to shrink transistors at an exponential rate, as Gordon Moore predicted in his famous law in 1965. And as you shrink transistors, it's historically been the case that they become cheaper to produce. The cost of each transistor has fallen roughly in line with their size. And they also become more energy efficient because they're smaller, so you need less electricity to operate them. And so you've had the combination of smaller transistors, more cost-effective transistors, and more energy-efficient transistors more or less running parallel from the early 1960s up to the present, with some changes as to which part of that process moves faster or slower. But that's been the 3 trends that have made Moore's Law possible. And they've been driven above all by improvements in manufacturing, improvements in design. On the design side, when the first chips were designed in the 60s, they were laid out by hand. You'd take a pencil, you'd draw on paper where you wanted the different transistors to be, then you'd by hand cut out a sort of wax outline of where the transistors would be, and then you'd use that to print onto silicon chips. Today, the design process is not by hand. If you got 1 billion or more transistors on chip, you need really complicated software to lay it all out for you and then to simulate it to make sure that the design will actually work when you put it on a chip. And so the software has gotten immensely complex over the past several decades, which is necessary to accurately lay out 1 billion or more components on a chip. Next to that, there's been an extraordinary set of machine tools that you use to produce chips. And today, there's a number of companies that make these machine tools, but 5 stand out. 3 are based in California, 1 in Japan, and 1 in the Netherlands, which make the tools that you need to produce each transistor, as you said, smaller than a coronavirus, with almost 100% accuracy by the billions. And so these machine tools themselves are some of the most complicated engineering feats in human history, using the flattest mirrors, for example, some of the most powerful lasers, and they're able to move individual atoms in some cases, layering on ultra-thin layers of chemicals or etching holes in silicon that are a couple of atoms wide. And so these tools have been crucial to the ability to print transistors that are so small with such accuracy.
For someone that studies theoretical physics that actually wants to apply his or her skill sets, is this the bleeding edge of where physicists are actually working today?
There certainly is a lot of advanced physics, chemistry, material science in the chip manufacturing process. But in addition to the science, and I think this is the important part, there's also manufacturing expertise, because it's not just a question of how can you make a process happen once in a lab. It's a question of how can you make a process happen 24 hours a day with basically perfect accuracy or 99.9% accuracy in a machine, in a fab, which is a chip making facility surrounded by all sorts of other explosive chemicals. And so the actual accuracy is just as important as the physics or the chemistry behind it. And that's, I think, what makes the companies that have mastered these machine tools particularly unique. They've found a way to convert the science into a replicable process that is cost effective. And that's actually the hardest part to do.
Yeah. So again, that reminds me of my conversation with Simon Winchester on precision engineering, because it's not just the ability to do something, it's the ability to do it over and over and over and over and over and over and over again at scale with near perfect accuracy. And the costs of getting it wrong are enormous. And the miniaturization for me is also something that, again, I'm thinking about that conversation with Simon, but here as well, it boggles my brain to understand how it is that human beings have gotten to this place where we're able to work at such scale. It's remarkable. How much know-how is required in this industry, and how big of an impediment is that to actually competing on a global stage? If you want to spin up a foundry or you want to spin up an integrated chip manufacturer. And actually, let me put that as part of a larger question around the characteristics of this industry. What are the parameters and incentives of corporate and state competition that inform the outcomes in this space? Things like product life cycles, capital requirements for both startup requirements and the ongoing capital requirements in the industry, consumer needs that drive production. What are those factors, and how do they determine outcomes in this space?
If you start with the end uses of where chips are going, who's actually buying chips, there's a couple of key customers. One is smartphone producers, and around a quarter of chips today end up in a smartphone, whether it's the processor chip that manages the operating software, memory chips, but also there's chips that manage the camera that can tell when your smartphone is vertical or horizontal, the Wi-Fi connection, et cetera. Around slightly less than a quarter of chips end up in a PC, processor chips and memory chips chief among them. Increasingly, data centers are huge customers of chips. So Amazon Web Services, Google Cloud, the big cloud providers are all consuming tremendous amounts of chips and will buy even more chips going forward. And then there's another quarter or so of chips that go to other types of devices. In automobiles, for example, most new autos will have dozens, if not a couple hundred chips, aviation, dishwashers, IoT devices, et cetera. And each end market has different requirements. If you want to put a chip in a smartphone, it's got to be very power efficient because battery life is crucial. If you want to put a chip in a car, battery life is less important, but you have unique temperature requirements because the car's got to operate in hot temperatures and low temperatures. So each use case has its own specific end requirements. But I would say that across use cases, there's a inexorable demand for shrinkage of transistors, and therefore increase in computing power, which has been basically constant throughout the industry. Not every chip requires more advanced technology and smaller transistors, but across the industry, that demand is very much there. And what that means is that there is always a market for smaller transistors and more advanced chips, which is why in memory and in logic chips, the two main categories of chips, the key firms are constantly racing ahead to produce the next generation. Because if you get to the next generation first, you've got chips that are around twice as powerful, consume less electricity, and therefore Apple will almost certainly buy them for the new iPhone. And so that has led to a market in which the machine tool producers, the companies that actually make chips, the foundries, and the software firms that create the software that design chips are on the same track as Moore's Law in driving forward shrinkage. And so they've got a guarantee that if they're able to bring the next level of technology to market, they will have customers for it. And so they pour lots and lots of money into this development. So if you want to make an advanced logic chip fab, for example, the type that would produce processors for an iPhone, it'll cost you around $20 billion plus or minus. And of those funds, around half will go to purchasing the machine tools inside the fab.
Is that every single year?
Not every single year, but every couple of years, because there are new generations of tools that will come online that So it depends on which tool you're looking at, but a couple of years per tool and you'll need to move up to the next level.
So is that for like a foundry like TSMC?
That's right.
So how much are they spending every year just to maintain their facility and to keep their equipment up to date and pay their employees, et cetera?
So the capital expenditures alone is many tens of billions of dollars every year.
Because I've seen numbers like 30 or 40 billion, numbers that are equivalent
it's
to the
more
cost.
Than that, yeah.
More than that.
Yeah.
To the equivalent to the cost of an aircraft carrier.
That's right. Yeah. A new aircraft carrier costs $10 billion. TSMC is investing more in CapEx every year than an aircraft carrier, and there's operating expenses on top of that. But the capital expenses are huge because you've got to buy the equipment and produce the facility. And so actually the operating expenses are less important in many ways than the capital expenditures, because once you have the equipment in place, once you have the facility in place, the cost of personnel, the cost of the actual silicon, the chemicals are relatively small in comparison. So it's the capital expenditure that's key. So once you've got a facility up and running, you can produce chips at that level of technology for the foreseeable future. And so TSMC has facilities that it built in the early 1990s that are still online. They've already depreciated all the capital expenditure, so they can produce chips quite cheaply. It's just the cost of the raw materials plus the labor cost. But the bleeding edge, the most advanced chips are hugely expensive because you've got to pay for the machinery and depreciate that over a couple of years.
Right, because you have to reinvest in new machinery every few years just to keep pace with improvements in the industry. How much of the market on a percentage term revenue basis is made up of leading edge chips that require those kinds of ongoing capital investments?
It depends a bit on how you define it, but around half of logic chips that you produce in revenue terms are leading edge, because you wouldn't make a smartphone processor or a PC processor or a data center processor with anything that's not the most recent generation or two.
So how much of the industry has moved from general purpose computing to building application specific integrated circuits, and how important has that transition been?
Yeah, it's a big shift that's underway right now. It's different if you look at memory versus logic or processor chips. Memory chips are not generally application specific. So it doesn't matter whether it's in your phone or in a computer. They basically the same with some changes type of memory chip. But for logic chips, we're seeing a lot more use of application specific chips, and we're seeing big consumers begin to design their own chips. So Apple designs its own chips for PCs, for its computers, for its smartphones. And increasingly big cloud companies like Amazon, like Microsoft, like Facebook are designing their own chips to optimize how their data centers function. And because they're huge customers for chips, they are able to get more power efficiency, more cost efficiency by designing chips that are specifically focused to the workloads that are in their data centers.
So that actually brings up something else, which is how this industry is broken into different parts or different models. So like I mentioned, the foundry model, which is what TSMC is, which is it focuses specifically on manufacturing. But you also have fabless companies that specialize in chip design. You also have companies that are, like you said, like Apple or Facebook, which have their own chips, but they're consumer electronics companies or social media companies. And then you have what are known as integrated device manufacturers, which are companies like Intel or Samsung. What is the difference between these models, and why is that important? How is it that, what are the incentives that have driven the industry to organize in this way? And how can we expect that model to evolve going forward, given some of the geopolitical dimensions that we've also talked about?
There's been a pretty, I'd say, steady trend in the industry towards more specialization. If you go back to the early days, Texas Instruments not only designed and manufactured their own chips, they also produced their own silicon wafers, the silicon circles on which chips are made. They refined their own chemicals in-house. They produced their own machine tools because there were no other firms that were producing them, so they had to build them in-house. Now, if you want to build an advanced chip, you need to buy chemicals and tools and software from dozens of different companies. And that specialization has been crucial in allowing firms to focus on what they do best and therefore drive technology forward in their particular sphere. And one of the key splits in the industry that began several decades ago and is still underway is the split between design and manufacturing. And so today, we've got a set of firms called fabless firms, fabless because they don't have a fab or a chip making facility, that solely focus on design. So companies like NVIDIA, one of the leaders in GPUs, the type of chip that's used in AI processing in data centers, or Apple is another example. They have chip designers who are very talented in-house that will design a chip and then send the file with the chip design over to a foundry, a company like TSMC, which doesn't design any chips, only fabricates them. And so TSMC will produce the chips that are designed by NVIDIA or Apple. Other companies like Intel is the best example in the United States, still do both design and fabrication in-house. And in the past, they've argued that there are efficiencies that come from that. They can optimize their production processes for the specific types of chips they've designed. I think it's pretty clear, though, that the benefits of separating design and manufacturing outweigh the costs, which is why companies like Intel have really struggled over the past decade to stay cutting edge both in design and manufacturing. Actually, they've fallen behind by a lot of metrics on both sides of that equation. Samsung as well has, I think, struggled, I would say, to keep its existing model functional. Samsung has a unique challenge because they have an electronics division that, for example, makes smartphones, and they also have a chip foundry that offers to produce chips for other smartphones. But the problem this creates is that Samsung ends up competing with its customers. So customers are very wary of going to Samsung and saying, hey, can you produce my smartphone chip? Because they're not sure what in that technology will end up in a Samsung smartphone a year down the line.
So is the reason that it's become increasingly difficult to operate the IDM model because the industry itself has become so complex and the process has become so sophisticated that being great at all the different steps is just not feasible?
I think that's part of the answer. Yes, it's just hard to be good at everything. I think next to that, there are huge economies of scale. And so the more chips you produce, the more you can learn from your existing processes to optimize future production. And the more you can get the rest of the industry to circle around you. So what TSMC has done over the past several decades is, because it's the world's biggest producer of processor chips, for the machine tool makers, it's their biggest customer. For the design software firms, they've got to have their design software optimized to work with TSMC. For intellectual property providers, they need to make sure their systems align with TSMC as well. And so the entire chip ecosystem has begun circling around TSMC. So TSMC is sort of the platform on which everyone else operates, which is great for TSMC because everything's optimized towards it. Intel, because it produces fewer chips and because it doesn't have this ecosystem around it, has had to struggle to get the rest of the chip design and chip machine tool customer base to focus on it. And so as a result of that lack of scale at Intel, which is still a very big company, but doesn't have the scale of TSMC, they've really had much more of a struggle to get the industry to focus on them the way the rest of the industry focuses on TSMC.
So let's talk a little bit about the production process here, Chris, because what I'm most interested in discussing is actually all the geopolitical stuff, but I feel like I just have to do this. And every time I think that we're almost done, I realize that I have so many more questions to ask. Walk me through the entire production process from the sourcing of materials to their assembly. So we're talking about raw material sourcing, research and development, design, manufacturing, assembly, testing and packaging, and distribution. What is that process and where does it happen and who are the biggest players in it?
Well, to start with the raw materials, if you want to make a chip, you need silicon, and not just any silicon, but ultra pure silicon. And there are a couple of firms that produce silicon wafers with the requisite purity, one in Germany, one in Taiwan, a couple in Japan. Then you need lots of specialized chemicals as well, where there are also a relatively small number of producers, again, largely in Europe and Japan for these chemicals. You take the chemicals and put them in a fab, but before you can begin operating them, you need to get a design. And so the designs for chips, as we mentioned, are often today made by fabless firms. Most of the big fabless firms are still based in Silicon Valley. NVIDIA, AMD, Apple, et cetera. There are a couple in Taiwan, a couple in China, and some for smaller niche cases elsewhere in the world. And designs are immensely complicated. If you want to design a chip in a smartphone, it could have tens of millions of lines in code. So it's a huge piece of software that requires, in many cases, thousands of engineers to work on and to test and to hone so that it works as efficiently as possible. And you've got to hone the design to get the power consumption you need, to get the speed you need. It's hugely important to have the best design. When you've got the design and you've got the raw materials, you send them to a fab, like one that's operated, say, by TSMC. And in that fab are these machine tools that we've discussed, produced by a small number of companies. And there's a couple of key steps in the chip making process. The first is called lithography, which is the process of shooting light in specific patterns at chips. And then the light will land on the chips and interact with a layer of chemicals that's put on a chip called photoresist chemicals. And these photoresist chemicals are sort of like what used to be used to develop photos. They're chemicals that react with light in specific ways. And so they'll either disappear when they're struck with light, or they'll harden when struck with light and allow the formation of structures on the silicon. And these are tiny structures at nanometer scale today. And so to layer chemicals like photoresists on chips, you need ultra flat layers that are very, very, very thin. And so this process of depositing thin layers with no variation is called deposition, from depositing. And there's a couple of firms that produce the right deposition machines. And then finally, you need to, where you've got a need to make indentations in the silicon, you need to etch chemicals away. So you have structures that are created, sort of like skyscrapers on the chip, where you've got some features that are tall, some features that are lower. And etching is the final major step, where you've got to etch with almost perfect accuracy little canyons, for example, in chips that are a couple of nanometers wide. And so this process of lithography, deposition, and etching is done repeatedly on an advanced chip. It can be done several dozens of times on the most advanced chips to produce the exact shapes that you want. And then finally, when it's done, you've got to test it and make sure you've done it right. And this is called inspection and metrology. And to do so, you've got to be able to see these nanometer scale structures you made on chips. And doing so requires really complicated microscopes and a lot of computing power as well to know what's the most efficient way to find potential defects. And so the companies that make the machine tools that do the lithography, the deposition, the etching, and the metrology have a crucially important role and constitute a major portion of the cost of actually making chips. And then finally, you've got the chips made. They need to be cut into pieces because they're all on a big circular silicon wafer. So you cut them into pieces and then you package them so they can be put in a device like a smartphone or a PC. And so from the time a design reaches a fab to the time a completed chip exits the fab, there could be 1,000 or 2,000 different process steps within a fab using all of these different tools and chemicals.
So I actually want to ask you what geographic regions are the most dominant and what companies are the most dominant in this chain. But before I do that, I don't think you mentioned where the resources are sourced. And this is actually really important because we often hear so much about rare earths and the importance of China in producing them. And when it comes to silicon, and especially gallium, China is central. I mean, I think the numbers I've seen are roughly 70% or so of the world's silicon production, at least in 2020, came out of China. And when it comes to gallium production, it was 97%. So I'm curious to understand, one, the specifics of that number. Is it still accurate? What is it? And two, why is that the case? Is it because that's where the reserves are, the deposits are? Or is it simply, is it a combination of that's where a lot of deposits are and the regulations have enabled their extraction in China?
Yeah, if you look at most of the materials and chemicals used in semiconductors, it's not that they're uniquely concentrated in certain parts of the world. So silicon is just sand. There's a lot of sand everywhere in the world. The question is, how do you get the most pure version of it? And that's a question of refining and production rather than a question of who's got the best geology for it. And I think what we've seen, certainly with rare earths, is that China has become a central, really the central player in the production of rare earths, not because of anything in Chinese geology, but because China's got the environmental laws that make it possible to produce rare earths in a cost-effective way. It's just dirty to do. And so we've sort of collectively decided we'd rather have that pollution in China, and China's happy to have that pollution in exchange for the business. Whether this represents a choke point or a risk, I think, is actually less clear. We know that it's possible to produce and refine many of these materials outside of China. The question is just at what price point and over what time horizon. We had a test case of this to a certain extent with one of the gases used in chip making, neon gas. Just this year. At the start of the year, around half the world's neon was sourced either from Russia or from Ukraine. And actually one of the biggest producers of neon gas was the steel plant in Mariupol, which was the site of so much of the fighting earlier this spring. And obviously that's not producing neon anymore. But there hasn't been any disruption to chips that's been appreciable, because ultimately neon is a tiny, tiny fraction of the cost of each chip. And so even if the price of neon doubles or triples or quadruples, you don't really see it in terms of the end price of a chip. And as prices rise, markets adjust, and other users of neon use less of it, and other companies that can produce neon start producing it. So we've actually seen a pretty efficient shift over this year in neon, despite Russia actively trying to cause production problems in chips. They haven't been able to use it. I think with other rare earths, there's a bit more leverage that China has because it would take a bit longer and be more expensive to adjust. But I'm skeptical that China's got a lot of leverage despite its huge market share in rare earths today, because it's just easier to get around those types of commodity choke points than it is to get around the machine tool choke points that the US controls.
So we'll probably touch on this raw material sourcing again when we get into the reshoring process. Two more questions related to this production process. One, I mentioned gallium nitride. From what I understand, the industry is looking to move collectively from silicon to gallium. What impact would a move like that have on the chip industry and efficiency and computing power?
So for certain use cases, there is a good reason to use materials other than silicon. So for example, in the chips that manage power supply, like in an electric vehicle, for example, where you've got a lot of power surging through an electric vehicle and complicated requirements for controlling power supply. There are semiconductors that use silicon carbide, for example, another material, to control that power supply. That's sort of a niche use. It'll be growing in importance as EVs become more important, but that's not going to replace the silicon chips in your phone or computer anytime soon, if ever. There are other uses in chips used for communication, for example, where other types of semiconductors can be more valuable, more effective. But I think that despite a lot of research underway, we're many, many years away from having non-silicon chips be at the core of the industry, precisely because all of the expertise in the chip industry is around silicon. All of the machine tools are designed to work on silicon. All of the engineers in fabs have built their careers around silicon. And so even if there are other materials that are theoretically better for certain use cases, the cost of change is just enormous because the entire industry has been built around silicon. And so I actually don't think we're going to be moving away from silicon in any sort of appreciable way for a very long time, if ever, just because the cost of transitioning would be so large.
So I read somewhere that of all the research and development done in the world, the greatest percentage of R&D spending happens in the semiconductor space. Is that correct? Is that still true?
If you look at corporate R&D spending, the only industry that is comparable is biotech and pharmaceuticals. If you look at R&D as a share of revenue, for example. Yeah, chip firms spend a ton of money in R&D because they've got to be rolling out new generations of technology every couple of years.
Yeah, that's amazing. So who are the last question on this front? Who are the leading SMEs, the semiconductor equipment manufacturers?
So in the lithography space, there's one company that has a absolute monopoly on the production of the most advanced lithography tools called ASML, based in the Netherlands. They've spent the past 30 years bringing online what's called extreme ultraviolet lithography, which is a lithography tool that has a specific wavelength of light that you need to build the most advanced chips. And so if you want to build an advanced chip today, you've got to buy their tools. There's just no choice. And their tools cost $150 million a piece, making them the most advanced and expensive machine tool in human history. So it's an expensive prospect to buy from them, but they've got pretty good pricing power, being the only producer of those tools. If you look at deposition equipment, Applied Materials in California is the market leader for etching, Lam Research in California, also Tokyo Electron in Japan. And then for metrology, KLA in California, also ASML produces a lot of inspection and metrology tools. But those five companies, ASML, Applied Materials, Lam, KLA, and Tokyo Electron, really have a dominant position in the machine tool industry, such that you really can't operate a advanced fab today without buying some equipment from all of them.
Last question before we move to all the geopolitics stuff and the geostrategic competition and the onshoring and all of that. How many years and how much time did you spend trying to understand this industry?
I spent the last 5 years doing nothing else but trying to understand this. It took 150 interviews and lots of reading in subsets that I had no knowledge of before I started to really make sense of it. And I think what is so cool about the industry is the extent to which no one in the industry understands the entire supply chain. If you're a lithography expert, the amount of years of study it takes to become a lithography expert in terms of the optics and the chemistry and the physics of lithography, you can't also be an expert in chip design at the same time. And so there are very few people, even deep in the industry, who have the bandwidth or the capability to step back and try to understand how the entire thing fits together. And so actually, as an outsider, it was enlightening in some ways to come in knowing very little about any of the steps and try to see how all the different pieces fit together, because all of the experts in the different subsets are so focused, rightly so, on their unique expertise. They often don't look up and think about the big picture.
Yeah, I mean, preparing for this conversation and having it also has made me feel so stupid. And it's really, I really struggled through it. And you can see just how much there is to learn. And for someone like me who has, I think, experiences information anxiety, I got a lot of it in the course of this conversation already. So Chris, I'm going to move us to the second hour on the premium feed. And like I said, this is the part of the conversation that I want to focus on, the geostrategic picture. I want to talk about the role of government subsidies, both Chinese state subsidies, which have been massive and massively important in helping the Chinese state achieve this accelerated development in this critical technology. I want to talk about the role of potential subsidies as well in the United States and what the U.S. is doing to onshore, to friendshore, to whatever term you want to use, to physically reshape the supply chain for semiconductors in order to achieve certain geostrategic objectives and economic and military resiliency. I also want to explore to what extent that's even possible, because in the course of reading your book and doing additional research, I came to the view that that may not actually be possible. So I kind of wonder what the real goal is. Is the goal to achieve some level of autonomy, to achieve some level of resiliency, though you can't make it foolproof? Is it to achieve autonomy in certain critical areas so that the United States can, for example, sustain a prolonged military engagement with China? We've seen, for example, how much the Russians have struggled. I mean, we talked earlier about the struggles that the Russian economy had during the Soviet period in keeping up with the U.S. technologically. But what we've seen also is that besides the fact that they've actually it looks like they've run out of munitions or certain munitions, they've also just had to rely entirely on foreign suppliers for certain key inputs to their military equipment. And actually, I think I saw recently that the U.S. government had to temporarily suspend the production of the F-35 because of one critical part that came from China. It was like a magnet or something, or some foreign supplier. So, I mean, we've built this world that's become so integrated, that leaned into efficiency and created so much wealth because of the end of the Cold War and the optimism of the 1990s and the unipolar moment, that talking about re-engineering that, it might sound easy or it might sound difficult but doable. But like I said, I really question just how doable it is and what we're really looking at here. So, I mean, that's just some of it. I mean, like, we're going to talk about all the different aspects of this stuff, how much leverage the United States has to actually do all of this, because these are private companies that are going to have to do all the heavy lifting to kind of do this. What steps have been taken so far? How, like, we can talk about the CHIPS Act, what types of regulatory incentives have and can be passed in order to make these changes. So we're gonna get into as much of that as we can in the second hour, Chris. For anyone who is new to the program, Hidden Forces is listener supported. We don't accept advertisers or commercial sponsors. The entire show is funded from top to bottom by listeners like you. If you want access to the second part of today's conversation with Chris, as well as the episode transcripts and intelligence reports, head over to hiddenforces.io and check out our episode library, where you can also become a premium subscriber today. Chris, stick around. We're going to move the second hour of our conversation, as I said, onto the premium feed. For more information about this week's episode, or if you want easy access to related programming, visit our website at hiddenforces.io and subscribe to our free email list. If you want access to full episodes, transcripts, and intelligence reports, which include additional notes, resources, links, and other material that will help you get the most out of each and every episode, check out our premium subscription, available through the Hidden Forces website at hiddenforces.io. Today's episode was produced by me and edited by Stylianos Nicolaou. For more episodes, you can check out our website at hiddenforces.io. Join the conversation at Facebook, Twitter, and Instagram at Hidden Forces Pod, or send me an email at dk@hiddenforces.io. As always, thanks for listening. We'll see you next week.